Alright, let's go. Number 10. The independent discovery problem. Historians of mathematics in the 19th century were doing something fairly dry. They were cataloging clay tablets pulled out of the sands of ancient Mesopotamia, mostly interested in trade records and tax lists. Standard model of history says separated cultures build separate knowledge systems, shaped by different languages. Different symbols, different gods. Contact explains agreement. No contact should mean no agreement. Then the tablets got translated properly. Babylonian scribes, working around 1800 BCE, had already worked out a method equivalent to the Pythagorean theorem, more than 1,000 years before Pythagoras was born. Plimpton 322. The tablet now sitting in Columbia University's rare book and manuscript library lists Pythagorean triples in a base 60 number system. Mathematics historian Eleanor Robson published her reanalysis of the tablet in 2001 in Historia Mathematica, and independent scholars in India, working in a completely separate tradition, arrived at the Sulba Sutras' version of the same relationship centuries later, again without contact. Every proposed explanation ran into the same wall. Trade contact? No documented route connects Old Babylon to Vedic India at the relevant dates. Coincidence? The odds of two isolated systems landing on the identical ratio by chance are close to zero. A shared proto-mathematics ancestor culture? No archaeological trace has ever been found. Each explanation required inventing contact that left no evidence anywhere. If two civilizations who never spoke to each other, never traded with each other, never shared a single symbol, kept independently bumping into the exact same numerical relationship, that relationship was already there before either of them showed up to find it. Which means somewhere in your own reasoning, right now, you are not inventing logic. You are discovering something that was waiting. What was it waiting in, before anyone existed to look? Nobody agreed to invent the same secret twice. Number 9. The late arrival of non-Euclidean geometry. Mathematicians for over 2,000 years were simply trying to prove Euclid right. Specifically, they were trying to prove his fifth postulate, the parallel postulate, followed logically from the other four, closing what looked like an embarrassing gap in an otherwise perfect system. Standard practice said every geometric truth described the one and only space that exists, flat, familiar, intuitive. Nobody suspected there was a second option hiding in the axioms. Carl Friedrich Gauss quietly worked out a fully consistent alternative geometry in which the parallel postulate simply failed. But he never published it, reportedly fearing the ridicule of what he called the outcry of the Boeotians. Jos Bolyai and Nikolai Lobachevsky independently published working non-Euclidean systems in the late 1820s and early 1830s. Lobachevsky's appearing in 1829 in the Kazan Messenger. Bernhard Riemann extended the idea further in his 1854 habilitation lecture at Göttingen, describing curved geometries with no parallel lines at all. For decades, the math community treated these systems as clever formal toys, logically valid but physically meaningless, because nobody could point to a real space that curved. Then in 1915, Albert Einstein needed exactly this mathematics, untouched and unmodified, to describe gravity itself in general relativity, built directly on Riemann's geometry. The toy turned out to be the blueprint for the shape of the universe, sitting on a shelf for 60 years before anyone needed it. Somebody worked out the geometry of a universe nobody had proven existed yet, using nothing but a pen and a refusal to assume the obvious. Right now, the space bending around every mass in the cosmos, including the planet under your feet, is running on math invented before physics asked for it. Why was the answer sitting there before the question was ever posed? The equations arrived first. Reality caught up later. Number 8. The Formalist Counterargument. David Hilbert, at the turn of the 20th century, was trying to rescue mathematics from a full-blown crisis. Set theory had just produced contradictions, paradoxes nobody could resolve, and mathematicians feared the entire discipline might collapse into inconsistency. Standard hope, going back to Plato, held that mathematical truths were discovered facts about an abstract realm, as real as stars, just not made of matter. Hilbert's actual proposal, though, quietly dismantled that hope from the inside. He argued mathematics needed no external truth to answer to at all. It only needed internal consistency, a set of symbols, a set of rules for manipulating them. And a guarantee the rules never produced a contradiction. Numbers were not things out there. They were pieces on a board, meaningful only because the rules said so. Hilbert formalized this program starting around 1922 at the University of Göttingen, aiming to place all of mathematics on this rule-based foundation once and for all. The failure parade started almost immediately. Gödel's 1931 Incompleteness theorem showed the program could never fully succeed, since any consistent system powerful enough for arithmetic contains truths the system itself cannot prove. Formalism survived Gödel by narrowing its claims, but it never answered the deeper problem. If math is only an invented game, why does an invented game keep predicting real particles decades before anyone builds a machine to detect them? If Hilbert was right, every mathematical proof you have ever trusted is just a very elaborate, very consistent game with no truth behind it at all, including the load calculations in the bridge you drove over today. Is the universe following the rules of our game, or did we just get lucky enough to guess its rules? Nobody has closed that gap since 1931. Number 7. The prime number distribution. Bernhard Riemann in 1859 was trying to solve a narrow, technical question about how many prime numbers exist below a given limit, a problem that had frustrated mathematicians since Euclid. Standard number theory treated primes as essentially random, unpredictable, scattered without any deeper structure connecting them, the mathematical equivalent of noise. Riemann instead found the primes were secretly governed by the zeros of a complex function, now called the Riemann zeta function, and that these zeros appeared to line up with disturbing precision along a single line. If that lineup held perfectly, prime distribution was not noise, it was structure, hiding in plain sight for 2,000 years. Riemann published the hypothesis in his 1859 paper On the Number of Primes Less Than a Given Magnitude, presented to the Berlin Academy. Every prime found since, and mathematicians have now verified over 10 trillion zeros computationally, has landed exactly where the hypothesis predicts. Every attempted proof has failed. Every attempted counterexample has failed. G, H, Hardy, Adel-Selberg, and dozens of Fields medalists have each taken a run at it across a century and walked away empty-handed. The Clay Mathematics Institute still lists it as an unsolved Millennium Prize problem, $1 million unclaimed since the year 2000. Prime numbers determine the encryption protecting your bank account, your medical records, and every private message you have ever sent, all resting on a pattern nobody invented and nobody can fully explain. If 165 years of the sharpest minds alive cannot prove why the primes behave, what does it mean that they behave anyway? The pattern does not need our permission to be true. Number 6. When physical constants in pure math collide. Paul Dirac in 1928 was simply trying to make quantum mechanics agree with Einstein's special relativity, a technical patch job to fix an equation that kept producing nonsensical results for fast-moving electrons. Standard physics at the time expected one clean solution, describing the electron and nothing else. Instead, Dirac's equation produced two valid solutions. One described the electron, the other described a particle with the electron's exact mass and the opposite charge. A particle nobody had ever observed, and nothing in physics said should exist. Dirac published the equation in 1928 in the Proceedings of the Royal Society, and the negative energy solution sat there, unwanted, purely a mathematical byproduct, for 4 years. Then in 1932, Carl Anderson, at Caltech, photographed a particle curving the wrong way through a cloud chamber under a magnetic field, exactly matching Dirac's unwanted second answer. He named it the positron. Antimatter had been sitting inside the algebra the entire time, years before anyone built an instrument capable of catching it in the physical world. Physicists tried to dismiss the second solution as a mathematical artifact, meaningless noise from the equation, an error to be patched away. That explanation died the moment Anderson's photograph hit the desk of the Nobel Committee, which awarded him the prize in 1936. Somebody solved an equation on paper and accidentally predicted an entire class of matter that did not yet have a single confirmed observation anywhere on Earth. Every PET scan in every hospital today runs on positrons Dirac found in ink before anyone found them in nature. How did the symbols know what the universe was going to do next? The math got there first. It always seems to. Number 5. The mind independence test. Philosophers of mathematics in the mid-20th century were trying to settle a much older argument, first posed seriously by Plato, about whether mathematical objects need minds to exist at all. Standard intuition, the one most working mathematicians quietly hold even without saying it out loud, assumes the Pythagorean theorem was true before anyone proved it, would stay true if humanity vanished tomorrow, and would remain true in a universe with no life in it whatsoever. Gödel himself, not just a logician but a committed Platonist, argued directly for this position, stating that mathematical objects are perceived by a kind of intuition functioning much like sense perception, giving us access to an objective mathematical reality independent of us. Gödel laid out this Platonist position most explicitly in his 1947 paper, What is Cantor's Continuum Problem?, published in the American Mathematical Monthly, arguing set theoretic objects existed as objectively as physical ones. Hilary Putnam and W. V. O'Quine later built the indispensability argument around the same idea in the 1970s, reasoning that since physics cannot function without mathematical objects, we are committed to believing those objects are real. Formalists countered that would remain true is an empty claim about a universe that, by definition, has no one left to check it. Nobody has produced an experiment that could ever settle the disagreement, because the disagreement is not about physical evidence at all. If mathematical truths do not depend on minds, they were true for the roughly 9 billion years the universe existed before any mind evolved anywhere to notice them, sitting silently correct in total darkness. Were the equations governing the very first stars already true before a single eye existed to read them? Nobody was there to check. They were reportedly right anyway. Number 4. Mathematical objects existing outside time. Georg Cantor in the 1870s was trying to solve a specific technical puzzle in analysis about which sets of numbers could be matched one-to-one with which other sets. Standard mathematical opinion at the time held that infinity was a single, vague, unusable concept, something to be avoided in rigorous proofs rather than measured. Cantor instead proved there were multiple different sizes of infinity, and that some infinities were provably larger than others, a result so disturbing to his contemporaries that fellow mathematician Leopold Kronecker attacked him personally and tried to block his publications. Cantor published his diagonalization proof in 1891 in the Jahresbericht der Deutschen Mathematiker Vereinigung, showing the real numbers form a strictly larger infinity than the counting numbers. The set of all real numbers, the continuum, apparently just sits there, complete and fixed, containing every decimal that could ever be written, whether or not anyone ever writes it. Kronecker's objection, that only whole numbers were real and everything built from them was human invention, failed to explain why Cantor's forbidden infinities kept resurfacing decades later in set theory, topology, and eventually the mathematics underlying quantum field theory. If the full, uncountable set of real numbers already exists complete, unchanging, and finished, then it was never assembled over time the way a memory or a sentence is. It simply is, the way your birth date is a fixed fact regardless of who remembers it. Where is a completed, endless collection kept, if nowhere in space or time was ever asked to hold it? Cantor called it a paradise. He also died believing it drove him mad. Number 3. Gödel's incompleteness theorems. Kurt Gödel, in 1930, was working inside Hilbert's own formalist program, trying to help complete the very project that promised mathematics could prove every true statement about itself, using nothing but its own internal rules. Standard formalist hope expected mathematics to be a closed, self-sufficient system, fully consistent, fully provable. No loose threads left hanging anywhere. Gödel instead proved the opposite was permanently impossible. Any mathematical system powerful enough to describe basic arithmetic will always contain true statements that the system itself can never prove, no matter how the rules are expanded. Gödel published the first incompleteness theorem in 1931 in the journal Monatschäfte für Mathematik und Physik, constructing a genuinely true statement encoded numerically that essentially says this statement cannot be proven within this system. The second theorem, published the same year, went further still. No consistent system can even prove its own consistency from the inside. Hilbert's entire program, the attempt to reduce all of mathematics to a closed formal game, collapsed within a year of its most confident public defense. Every attempt since to patch the gap by building a bigger, stronger system has failed the same way. The new, larger system simply generates its own new, unprovable truths, an infinite regress with no floor. John von Neumann, present at the 1930 conference where Gödel first mentioned the result, immediately recognized its severity and told colleagues formalism was finished before Gödel had even formally submitted the paper. If true statements exist that no system built by any mind, human or otherwise, can ever fully prove, then truth is larger than proof itself, larger than logic itself, larger than anything a symbol system could contain. What true things about your own existence might be permanently unprovable, even in principle? Gödel proved the wall exists. He never told us what's behind it. Number 2. The unreasonable effectiveness problem. Eugene Wigner, in 1960, was not trying to start a philosophical argument. He was a physicist reflecting on his own career, on how often equations built for pure aesthetic or logical reasons, with zero interest in physical application, later turned out to describe reality with staggering precision. Standard scientific assumption treats mathematics as a tool humans built to model the world, a language shaped by usefulness, expected to fit only loosely, and only where we forced it to. Wigner instead documented case after case where the fit was not loose at all. It was exact, unreasonable, and arriving decades ahead of any application. Wigner published his argument in 1960 in Communications on Pure and Applied Mathematics, under the title The Unreasonable Effectiveness of Mathematics in the Natural Sciences, pointing to complex numbers, invented in the 16th century purely to solve algebra puzzles with no physical meaning, later becoming indispensable to quantum mechanics in the 1920s. Group theory, developed by Varist-Galois in the 1830s to answer a question about polynomial equations, turned out to describe the fundamental symmetries of particle physics a century later. Every counterargument proposed that scientists simply cherry-pick the mathematics that happens to fit, that failed models are quietly forgotten while successes get remembered, fails to explain the sheer precision of the fits that do work, corrected 10 or more decimal places in cases like quantum electrodynamics. If mathematics built with no reference to reality keeps predicting reality anyway, then either the universe was built out of mathematics to begin with, or mathematics was somehow always eavesdropping on a universe it had no access to. Physicist Roger Penrose has called this connection almost mystical. He has never offered a better word. What is math listening to that lets it hear the future of physics before physics gets there? Number 1. The unresolved divide. Philosophers of mathematics across the past century. From Gödel's Platonism to Hilbert's formalism to intuitionists like L.E., J., Brouwer, were each trying to finally settle what numbers actually are, once and for all, so the rest of mathematics could stand on solid ground. Standard expectation, going back to the earliest debates, assumed one side would eventually produce a decisive argument and the question would simply close, the way most open scientific problems eventually close. It never closed. After roughly 2,500 years, running from Plato's Academy to modern university philosophy departments, there is still no consensus on whether the Pythagorean theorem was discovered, sitting out there in some non-physical realm waiting to be found, or invented, a rule of a very convincing game with no reality behind it. Every major position has been defended by working mathematicians with impeccable technical credentials, and every position has been attacked with equal rigor. Platonism explains why independent civilizations and independent centuries keep landing on identical truths, but it cannot explain where this mathematical realm physically is, or how a human brain, made of ordinary matter, supposedly reaches into it. Formalism explains why mathematics is just internally consistent symbol manipulation, but it cannot explain Wigner's problem. Why an arbitrary game keeps predicting real particles before real particles are ever detected. Intuitionism restricts mathematics to what can be constructively built, but it throws out large parts of the number system every practicing physicist relies on daily. You have been using this unresolved tool since childhood, in every measurement, every calculation. Every piece of engineering keeping the building around you standing upright, without ever needing to know what it fundamentally is. If nobody can say whether numbers are discovered or invented, what does that say about the mind doing the counting? That question was already old when Plato asked it. It is still open tonight. 10 separate collisions. 10 separate decades. 10 separate fields, from ancient tablets to quantum electrodynamics, and every single one lands on the same fracture line. The universe is not confused about what mathematics is. We are. Every equation on this list sits not at the fringes of human knowledge, but at the load-bearing center of our most tested, most trusted theories, the ones running your phone, your GPs. The hospital down the street. We built civilization on top of a tool, and after 2,500 years, we still cannot agree whether we made the tool or simply found it lying there waiting. Maybe the most unsettling part is not that the question stays open. It's that it doesn't need to be closed for the math to keep working anyway. If you want to see more videos like this, click the video on screen now.